Hi, welcome to the lecture 17 where we talk about the Gauge Principle and QED, quantum electrodynamics. And last time we saw that a global transformation of the Dirac field psi by a constant phase theta that has no space-time dependence induces a conserved nether current J mu of the form psi bar gamma mu psi. Well, but we still believe that locality is a strong principle of nature and it's worth exploring what happens actually when we make the generator of the rotations space-time dependent. That means essentially if I have a space here, then this theta angle can be different in each place and space, right? So you have different theta transformations in each position in space, and also it could vary with time. Now that we can ask the question, what will be the case? Will the Lagrangian be still invariant under such a transformation, where now my phase rotation has actually angular space-time dependence? Now the psi bar psi combination in the Lagrangian will be invariant because we can just pull out the exponentials and things cancel and we just get a factor equals to 1 here. So this term is invariant, that's fine. But a combination that contains a derivative of this form, d mu psi, where we have this part that gives us the exponential with a negative sign, when we have a part that is indeed invariant, where the derivative acts on the field, but the exponential is not affected, where these things cancel. There we get a part that seems invariant, but we also get a part where the exponential, where the derivative acts on this exponential here, and we get e d mu theta term that multiplies this current. And this is a non-invariant part, so the whole interaction seems non-invariant. However, we can introduce a local compensator field, or a gauge field, A mu, which is, well, simultaneously we can make the Lagrangian invariant when we make this field transform simultaneously with the derivative of the phase rotation phi, that is space-time dependent, and, well, we have this factor up front here, and we introduce the so-called covariant derivative, d capital mu, which is just the normal derivative plus i.e. a mu, and here we have this gauge field a mu. Now let's see what this new term, psi bar d slash psi, how that transforms. So this is the expected term that we have seen. This is the term that we found comes from the derivative acting on the phase shift. So that made our life difficult last time. And this is the combination where we have the a mu field multiplying the psi bar gamma mu psi combination here, coming from here and multiplying the psi's. And its transformation, as we said, is related to the transformation of the gauge field itself under the phase rotation, and it exactly cancels the contribution that actually is bothering us. So then this term again is the same as we started with. So this term is we restored the invariance of the Lagrangian by introducing a new compensator field. This leads us actually straight to quantum electrodynamics, and in fact this a mu compensator field is nothing else but the photon field. Now the QED Lagrangian has the mass term for the fermions, and this kinetic energy term contains the kinetic energy of the fermions, but also the interaction with the photon through the covariant derivative. We have a mu multiplying the electron current J mu. So we have already discussed how currents can source interactions. This is exactly the term that now is responsible for coupling of the electromagnetic current to the photon field. The only thing that I denoted here as L gamma that is still missing is the kinetic term, the kinetic energy term for the photon field. And we expect, by analogy to the Klein-Gordon scalar field, that we have something that goes like square in the derivatives of the field A. However, like a term of this type, where we would contract, for example, the indices of A with itself and the derivatives here mu with itself, is not gauge invariant, so it's not invariant under the transformation that we introduced. However, we can define a new structure, the so-called field strength tensor, field strength tensor because it has two indices mu and nu, and it is an antisymmetric combination of the derivative and the photon field, d mu a nu minus d nu a mu. It transforms, luckily, in a good way, because here we can say that it goes to, we can plug in the transformation properties of the A field here. So we have d mu A nu minus 1 on E d nu theta here, and this goes to d nu, this term goes to d nu A mu minus 1 on E d mu theta. So now if we write it out, we have from those two contributions just the F mu nu term itself, and then we have a combination where we have a difference between d mu d nu theta minus d nu d mu theta, but we can swap derivatives through each other, so we have here twice the same term subtracted from each other and gives 0. So this tensor is also invariant under gauge transformations, and we can use it if we take its product, basically contracting the indices with the appropriate prefactor to compensate for 4 possible contractions here. We get actually a well-defined kinetic energy term where we have d mu, essentially d mu of the A squared terms. Good, so this is our kinetic energy for the photon, and we know also that the A mu in fact transforms as the Lorentz vector, where the mu index is indeed a Lorentz 4 index, and it represents a spin 1 field, and as it's an even spin field, it is a boson. Well, the A mu is in fact identified with the potentials. So the zero component is the electric potential, and the spatial component is the magnetic vector potential. F mu nu also has a related object, the dual field strength tensor, where we contract the field strength tensor with this epsilon absolutely antisymmetric fourth rank antisymmetric tensor. It's related to the epsilon ijk absolutely antisymmetric tensor. And by construction now we can find an interesting, from this construction we can find an interesting identity. Applying the derivative to the dual field strength tensor, we can explicitly write it out, having here the derivatives acting on A from the definition of the field strength tensor. We pull out the antisymmetric tensor up front, and then we pull the derivative through. Since the tensor is not affected by a derivative, we have these two expressions, but we can do cyclic permutations of the indices, as it doesn't affect the plus or minus signs in this tensor. So we can swap those through. Like if you have mu rho lambda, we can make a cyclic permutation and send lambda here, mu there, and so lambda here, mu there, and rho there. So we have mu rho lambda, and now we have lambda mu rho, those two identical under this transformation, and we can swap the order of the derivatives as derivatives commute, and we have twice the same term again that cancels. So this derivative of the dual field strength tensor is 0, and we will see why it is useful in a little bit. Now let us now find out what is actually hidden in these field strength tensors. For example, remember the electrodynamics definition that the gradient of the electric potential minus the derivative of the magnetic potential in time is the electric field, and the rotation of the magnetic potential is actually the magnetic field. Now by construction, the F mu mu, the diagonal terms are all 0. The F spatial component and temporal component combinations that have the derivative spatial derivatives of the zero components, which is essentially the divergence of the scalar electric potential minus the time derivative of the vector potential, which is just the E field, and the pure spatial ij components are absolutely antisymmetric combinations of the derivatives of the magnetic components, which is just the rotation of the A field that is equal to the B field. So we can now write out the field strength tensor in the temporal component. It has the electric fields with the minus sign in this row, in this column, and in the spatial components it contains the B fields in an antisymmetric combination with the appropriate minus signs. And the dual field strength tensor here, if you go from the field strength tensor to the dual one, it swaps essentially the E and B fields and add the minus sign overall. So now we have here in the time component the B fields and the spatial component the E fields. As we said before, the total derivative of the dual field strength tensor is 0. So if we evaluated it on this, what it means on the temporal component, we essentially see that this is just the divergence of B that has to be 0. And the other components on the spatial components running over the like on the spatial components running over the derivatives over time and space, contracting the mu index, evaluating those combinations in the vectorial form, gives us the rotation of E plus the derivative of B is equal to 0, right? So we evaluate essentially these values here by contracting over the derivative index and taking the spatial vector indices. And this is just the second homogeneous Maxwell equation. So we see the homogeneous Maxwell equations are not even coming from the equations of motion, but just by construction of the dual field strength tensor. And they are essentially a consequence of the covariant or the Lorentz invariant, fully Lorentz invariant formulation of the electromagnetic field equations that really enforce the homogeneous Maxwell equations on us. The variational principle of the QED Lagrangian, however, gives us derivative of the field strength tensor is proportional to the electromagnetic current, given by psi bar gamma nu psi. And if you look at it in components, the zeros component, taking nu equal to 0, gives us the divergence of the electric field is equal to the electric charge density, and the rotation of the B field minus the derivative of the electric field is equal to the electric charge motion of electric charge. So this is the electric current in the spatial components. If we look again at the physics that is implied by that, is the first equation here means that the electric charges give us divergent field lines coming from them. And this is known from electrostatics. The second equation is also important really in electrodynamics, where we have moving charges that induce a change of electric fields, obviously, but also induce a rotation in the magnetic fields around them. Finally, this equation 3, here from the homogeneous Maxwell equations, the divergence of B is 0, implies that there are no particles in nature that lead to divergent magnetic fields coming from them. And that means that we haven't, or at least we haven't found any of those so-called magnetic monopoles that act as regions where magnetic field lines diverge. That doesn't exist. So they always have to run in closed loops because of some, essentially because of some charge motion. Finally, this equation 4 is the induction law. So if we have a changing magnetic field, it induces a rotation in the electric current in the conductor, for example. So having a B field change in this direction that runs through a loop of electric conductor induces a running of charge here, so it induces an electric field in the charge motion. This is the principle behind the induction stove or the electromagnetic pulse that can damage or destroy electronics. Well, now after this recap of the electrodynamic principles, we can go to the evaluation of Feynman rules for quantum electrodynamics. And I can't really derive them due to the lack of time, but I will quote them and show you how to use construct amplitudes using these diagrams. So now first we have to draw all allowed diagrams assigning momenta to external particles and integrals over internal momenta, as we said before. Lines conserve charge, as in the case of charged scalar fields, and the flow follows the arrow direction, as also for the complex scalar. So the interaction vertex that is important now, a new important direction vertex, is this one that comes from this interaction from psi, gamma mu psi in the photon field A, and it's drawn as a line of fermions going through, and they can emit or absorb a photon field here. Now, we can finally read off the amplitude reading against the charge flow direction. We will learn this in a second. But the rules that we have to follow are based on external lines first. If we have incoming particles that are electrons, we have an incoming particle to a vertex that gives us the spinor u without a bar. If we have an incoming positron, it gives us a spinor v with a bar. We have to remember this rule. And the photon incoming particles gives us a polarization vector e mu. Right? The photon has the a mu has a 4 index, so this polarization tensor has also a 4-dimensional index, space-time index. If you have an outgoing particle, an electron as an outgoing particle, you have a spinor u with a bar. If you have an outgoing positron, antiparticle, we have a spinor v without a bar. Also, an outgoing photon gives us the polarization vector e mu, which is conjugated as also, since it gets complex. Well, now coming to the propagations. For the fermion propagator, if we connect 2 points by a fermion line, the propagator is given by the known term, like the denominator is still the same, k squared minus me squared, but from the Dirac equation we know that the kinetic term has only one linear derivative, so the propagator is somewhat different and has a mass dimension 1 part in the numerator, so which is equal to the momentum k multiplied with the gamma matrix plus the mass of the electron. So it's k slash plus me in the numerator. It's quite a special case and needs quite careful evaluation in amplitudes. The photon connecting 2 lines also goes as 1 divided by k squared, the momentum squared. There is no mass involved since the photon has no mass. And in the numerator it has the metric tensor eta mu nu, and we will see in an example how it is used in amplitudes. Finally, the vertex, as I said, from the interaction of a mu, j mu, leads to a gamma mu matrix in the amplitude times negative I, E, which is the electric charge unit, times Q, that is the electric charge of this particle. I mean, for electrons and positrons, this is just 1, essentially. For electrons in particular, it's -1. If you have quarks or other particles, they could have in principle different charges, 1/3 or 2/3 and so on. So this is the electric charge unit here. The electric charge unit, E, and Q is the electric charge of the particle. Now let us look at an example process, which is E plus E minus, positron-electron annihilation, that produces heavier versions of them, muons or anti-muons. So this is the diagram. It's a pure S-channel diagram where we have exchange of a photon that carries the momentum P1 plus P2 of the incoming 2 particles. As I said, we read out the diagram reading against the arrow flow. Let's start here with the positrons. So we have an incoming positron, so we have and go against the arrow. So we have V bar, as we said, times now the vertex is QE gamma mu here, and an incoming electron, which gives us a U without a bar. Now we have a propagator that is here, the Minkowski metric tensor divided by the momentum squared, and the momentum is P1 plus P2 squared. Now here again we go now against the flow of the arrows. We start with the outgoing muon, and we get the U bar from the outgoing particle. Now there is the interaction vertex QE gamma nu, and then outgoing antiparticle that gives us the spinor V without the bar. We also have spin indices here that we will not discuss in more detail, but they are actually relevant later for the evaluation of amplitudes. In particular, the spinor indices mean that we can have, if we look at we can think of this process in the helicity basis if we assume the total energy to be much larger than the masses, and think that the particles are really controlled by chirality is equal to helicity. We can in particular have states that have helicity of the projection of the spin going in the direction of motion or against the direction of motion, that is plus and minus helicity. So we have 4 different combinations that are non-zero of this interaction. So for example, we could have a plus-minus electron-positron meeting and producing a plus-minus helicity mu and anti-muon pair. And the amplitude in this case is proportional to the E squared divided by the momentum sum squared, and that cancels this 4e squared actually. So we get nothing else but e squared times 1 plus cos theta from this amplitude. And in the end of the day, summing over all non-vanishing amplitudes, which is the plus minus minus plus helicity, minus plus plus minus, and minus plus minus plus combination, we obtain the total cross-section. Adding them and squaring those amplitudes gives us the total cross-section. It goes as 1 plus cos theta squared, and the prefactor is alpha squared over 4e squared, of where e center of motion is the center of motion energy of the system, and alpha electromagnetic is the electromagnetic coupling constant, as we discussed, equal to the coupling strength e squared divided by 4 pi, which is just convention. The integrating over the cos theta term gives us the total cross-section. Actually, that's 4 pi over 3 alpha squared over e squared. But we can also plot the differential cross-section as a function of the angle and see that it's maximized at theta equal to 0 and minimum at theta equal to pi minus pi half and pi half. In a sense, it means that if you collide e plus and minus, that the most probable outgoing particles would fly along the direction of flight, continue basically straight, and the probability is lower when you go perpendicular out of this process. For the evaluation of the amplitude, more complicated trace techniques are needed, and they're well described in a book, for example, Peskin and Schröder, that you could definitely read on your own and familiarize you a little bit with the trace technologies, which I would recommend. However, we don't have time to go through the trace technology in this course. Now let me summarize what we have learned and discovered so far. We looked at different types of spin particles. So one type is that we talked most about is spin zero particles. They don't have external indices, only the arguments transform under Lorentz transformations. They're called scalars or spin zero particles, and they're bosons. We follow the Boson statistics as we discussed. Then we also have particles with 2 internal degrees of freedom that transform both as a spin 1/2 units. So this is this Dirac spinor with psi L, psi R components, and they're fermions. They follow the Fermi statistics. There's also the local gauge invariance that we discussed today that leads us to introducing a new field that has a 4-component index and really transforms as a vector under Lorentz transformations. Here they're being multiplied by a Lorentz matrix, and it has spin 1. It's also a boson. The most common example is the photon. There are also 2 more other options in QED for spin. For example, the spin 2 particle. It's essentially a tensorial field with 2 indices, and the field that is related to it, to this spin 2 field by the so-called supersymmetry transformations. This is a spin 3/2 fermion, while the spin 2 is a boson. So those 5 options of spins exhaust the menu of particles of different spin that we can have in quantum field theory. Other higher spin theories are not really well defined. This is one interesting result. And another result is like, what are the possibilities to make those fields interact with each other? There are not that many either, especially from the renormalizable interactions that are most relevant at lower energies, as we saw. Before hitting something like the Planck scale, we, let's say, can ignore contributions to physics that come from these higher, highly suppressed operators that are non-renormalizable. So the relevant operators for us would be, for example, the phi psi gap psi is the interaction of one real scalar and charge scalars of this type, 3 fields. We could also have a very similar scalar fermion interaction, which is usually called the Yukawa interaction, with the real scalar and 2 fermions. Then we could have scalar self-interactions, phi cubed, phi to the 4, 3 and 4 fields with each other. Or you could have interaction of the photon field with the electromagnetic current, as we derived today. So it's a photon, vertex of the photon talking to fermions, electrons, positrons, and other fermions. And you could also have the photon field being coupled to the charge, to the current of the complex field phi, which we showed in quite early lectures that the conserved current there is phi star d mu phi, actually minus phi d mu phi star. So They're like an additional combination, but the structure of the interaction is the photon A mu field is constructed with the derivative of the phi star phi combination. Again, it's a three-field interaction with the momentum, with a derivative, so which adds in the momentum space essentially a power of momentum, and is a velocity-dependent interaction of vector fields with scalars. So it's also a three-field coupling. There are also vector self-interactions that could go as this, cubic, three vectors together, so it's something like a cubed or a to the 4 with the appropriate index contractions, is possible in so-called non-abelian gauge theories. So this is, we also have 3 and 4 vector fields coupling with each other. But now we see that the QFT menu of our Lego building blocks is actually quite small, and as soon as we are moved beyond effects of effective theories and resolve the fundamental interactions, we really see that those ones that are interactions that are relevant for a long range of energies that are, let's say, above the effects of complex fields interacting with each other in a non-perturbative way, such as the QCD, the strong interaction of nuclei. Once we are beyond those interactions, essentially when we enter perturbative QFT regimes, these regimes are very simple, the theories are very simple, and the ways the fields interact with each other are very limited. The menu of fields we have is very limited, and that makes nature actually quite well describable by QFT at those large energies. And this is quite a beautiful principle of the quantum field theory that we have. Well, overall, this brings us to the end of this QFT course 1. And the next two lectures, essentially, we will use to discuss a more advanced topics such as introduction to the standard model of particle physics, and a little bit about, we will also discuss in this context non-abelian gauge fields, but this will be done in a more introductory way to prepare you for the next advanced QFT lectures.